Hi, I'm Takhya Holley. I am starting my first year as a PhD student at the University of Texas at Arlington in chemistry with my supervisor, Dr. Cole. So I'm currently working on kinetic analysis of pyrolysis of polymethylhydrosiloxane cross-linked with divinylbenzene. So to conduct my kinetic studies, I'm using thermogravimetric analysis, TGA. So we know that TGA continuously measures mass of a material as a function of temperature, whether this is done isothermally or non-isothermally. So I'm using TGA to look at, to study the thermal decomposition involved in pyrolysis of PMHS cross-linked with DDB. So first I obtained my TGA. So this is the 50 degrees Celsius per minute heating rate. So I have, looking at the TGA on the left, it appears that I have two mass loss events occurring. One from ambient to about 200 degrees Celsius and another one occurring about 350 to 1,000 degrees Celsius. I'm more so interested in looking at the derivative of DTG, which is telling me how many processes I have occurring. So looking at the DTG, I have 1, 2, but I also have this little shorty here indicating that I have some other process. So for this, I will be varying my heating rates and using the variance in my heating rates in order to determine kinetic parameters. So from your own data that you may have seen, whenever you vary the heating rate, then you see shifts in your TGA curves or your DTG curves also. So as you increase your heating rate, we have 210, 50 degrees Celsius per minute, you see a shift to the right or a shift to a higher temperature for your thermal processes, which we also see here in the DTG. So I'm interested in looking at the pyrolysis of the system. So I'm only looking at from a temperature range of 300 degrees Celsius to about 1,000 degrees Celsius. So to do this, I'm using isoconversional model-free method in order to determine my kinetic parameters. So typically when you do, when you're looking at kinetic parameters, they treat the pyrolysis as one step. So you obtain only one activation energy typically, even though you may have multiple reactions occurring. So we're using the isoconversional model-free method, which this method considers the degree of, it treats the data as an infinite number of processes. So there can be infinite number of independent parallel reactions happening versus just treating the data as just one reaction, the pyrolysis is one reaction. So this method, this isoconversional method, assumes that the activation energies, which is what I'm determining right now, the activation energies are only dependent on the degree of conversion instead of the actual heating rates themselves. So first, we would determine the degree of conversion, which is alpha, where here we have is shift essentially the mass block in percentage form from this 300 degrees Celsius to 1,000 degrees. So our M sub 0 is our initial mass, M sub T is our mass at that time, and then the M sub infinity would be the final mass. So the standard reaction rate equation that is used for the change in conversion related with respect to time is here, this equation here, where the second equality assumes that it's separated into a product, which is a temperature dependent function and then some function of alpha. So this f of alpha here is described some kind of reaction model. So here are two different examples of reaction models that are used. So from here, this Temperature dependent function is an Arrhenius type function, which you will see here, which allows for the determination of the activation energy. So for a non-isothermal experiment, such as CJ experiment, at a certain heating rate, this is the equation that you use for the rate of conversion, which is used for these model-free methods. You can use these for peak fitting, or there's multiple model-free methods that you can use also. So the system I'm using. So I cross-linked this PMHS with this EVB with the ratio of 1 SiH to 4 vinyl molar ratio with a 1% total of catalyst. And so I'm using heating rates of 210-50 degrees Celsius per minute. And then I'm also, something that is very important when you're doing kinetic studies is that I'm using a catalyst. So the time from synthesis to analysis must be identical. So for my 50 degrees Celsius per minute, my analysis will occur 21 hours from synthesis. For 10 degrees Celsius per minute, my analysis will occur 23 hours, and then for 2, it'll be after 40 hours, which I keep all of these constant. So the Freeman differential isoconversion method essentially just is a linearized form of the third equation, which will allow for me to calculate the activation energy. So I would take the natural log of this d alpha dt, graph it inverse temperature, get the slope, and then I have my activation energies, which I would do them at different degrees of conversion. So for my activation energies, here we have our degree of conversions, and then we have the activation energies that were calculated from each one of these. So you'll see here, looking at the data, going from 10% to 80%, you see a steady increase in your activation energy, but when you get to 90% conversion, you see a huge jump in the activation energy. So what is this telling us? This is telling us that at some high temperature, there is another process that is occurring there. And there is also an overlapping process. Now, whether this process is happening simultaneously or consecutively is another question, but there is some other process that is happening. So for my future work with this, I've only been working on this for the last 2 months, but my ultimate goal is to do kinetic analysis with different porosity. And I would like to essentially differentiate the diffusion processes from chemical processes.